All right, well, this lecture is more about positioning a collector and trying to make it work out right. Or if you have a certain position of collector, how good is it going to do as far as collecting? So, collector surfaces can be a variety of angles. So let's just imagine that this surface right here is a collector surface. It could be a PV cell, it could be a solar thermal, et cetera. It could be a window. There are some interesting systems where we say, hey, we're going to treat a window like a solar collector. So in any case, when we think about how it's going to be positioned, we're going to think of it how we're going to position to the normal line. So in this case, this is a horizontal surface, and we've got the normal line facing up. If we went to a vertical surface, the normal line's obviously going to be going out like that. And then here in Sacramento, I was telling in the last lecture, the surface is a lot of times like about a 40-degree tilt. So I didn't get that really well positioned there, but then the tilt of around 40 degrees works pretty well. All right, so we're going to practice that a little bit today and get better at the math. And let's get some nomenclature up there and have what we have so far. So basically, a lot of cases, the information that you have available is to know the intensity of the direct solar on the horizontal. And we would like to get how intense it is on the surface normal. So let's just say that blue is one of many different angles of solar coming in, and it's coming in at an angle of alpha, let's call it 30 degrees above the horizontal. And obviously, we had the idea last time that if you had a surface that was perfectly perpendicular to it, a surface like that was perfectly perpendicular, the intensity would be higher. And here's our formula for that. So to get this intensity of a surface that directly faces the incoming solar direct rays, you can take GDH and divide it by sine alpha. So that's old news. Okay, what does theta stand for? That was a little bit new last time. Theta is the angle of incidence between some incoming solar and the collector, where the incidence is relative to the normal line. So if I took this, there would be many different rays coming in here, all horizontal. That's one idea that we had. And if I take this ray here and put it right in there like that, and that would be, I'm intending that new blue line to be parallel to the original blue line. The angle of incidence would be the angle between this line here, there like that. So that's the idea of our angle of incidence. And then we finished up last time by saying, hey, how are we going to get the direct on some sort of tilted surface? So you could think of this as the direct radiation on a tilted surface. The book tends to drop the theta. And what we can do is we can take the normal direct and multiply it by the cosine of the angle of incidence. And that, again, was in last lecture. One other thing that came up last lecture was we talked about beta. Okay, and beta would be the tilt of your collector surface. I have it in that drawing right there. Beta equals 0 degrees would be not tilted at all, and beta equals 90 degrees would be a vertical surface. All right, so just with that, we can do some pretty good practice. Let's just go ahead and do some really, really simple examples where we go through and say, hey, what is the intensity of the solar on a surface going to be? All right, so the math is really, really easy. It's just basic trig, but the challenge is figuring out the angle of incidence and sort of interpreting what's going on. So let's just practice with the angle of incidence a little bit. So imagine that this is our collector surface right here. Here's our normal line. And let's just do, let's figure out the angle of incidence if alpha is equal to 20 degrees. So this line right here is supposed to represent the south direction. So towards you guys would be west and towards me would be east. Alpha equals 20 degrees. I didn't specify where the sun is. So I'm just going to go ahead and imagine that these are the sun's rays coming in. There would be sun's rays hitting everywhere on that collector. And they're all going to be, the direct beam radiation is all going to be parallel. Okay, so 20 degrees would be 20 degrees above the horizontal. So a pretty low angle there like that. Okay, and just take a second and visualize alpha and visualize theta. So hopefully you got it. This is 20 degrees. Theta is the angle between the normal and that, so theta is 70 degrees. Okay, what if it was 20 degrees and the sun was more towards the southwest? Okay, so the sun was over here like this. Well, that's still 20 degrees and that's still 70 degrees. So basically what we have in this case for a horizontal surface, the angle of incidence theta is 90 minus alpha. And you can use that sometimes for really simple cases. All right, the next most simple case, getting going on it. What if you had a vertical surface? Okay, what if you had a vertical surface? And there are collectors that are vertical, and obviously the most common vertical surface that we're interested in is what if we have a window? So bear with me, I'm not holding it super precisely well, but hopefully you get the idea. So let's go ahead and again envision alpha is equal to 20 degrees. What is the angle of incidence going to be? So try to maybe do a quick sketch on your paper or just visualize it, and here we go. So again, the sun is low in the sky, alpha is 20 degrees, okay? It's hitting here, it's hitting here, it's hitting here, it's hitting here, and it's hitting right there like that, okay? So alpha is the angle between the horizontal and the incoming, the angle that, alpha is the angle between the horizontal and the incoming ray. So alpha is that angle there between that metal screw, okay, and the dowel, which represents the sun. So alpha, I got alpha right in there, and that is also the angle of incidence. So the angle of incidence would be 20 degrees. All right, okay, let's do a higher tilt, okay? So pardon me, a higher alpha. So let's say the sun's really, really high in the sky, like 80 degrees. Okay, well, it's going to be hitting there, 80 degrees, and including right at that particular normal line. So where there's 80 degrees between the normal line and the incident radiation. So those are two really, really simple cases. If you have a horizontal surface and you have a vertical surface, and let's just do one example really quickly with that to make sure we're on track with how the numbers work. All right, so first example to take a look through. So I would encourage you just to read through it and see if you can make sense of it yourself, and then we'll get working on it. So I've given you some data about solar. That's pretty low, 200 total. The diffuse is 40. And the sun is in the south. The gamma is the symbol that's often used for the direction that the surface faces, or the direction that the surface faces. So that would be gamma is equal to 0 degrees, would mean that in the plane that this surface faces 0 degrees. So if that direction that way is south, this surface is facing south right now. So basically we got a surface facing south. Even if this surface were tilted, if we took the component of the normal that's in the plane, it would be facing that way, it'd be south. So this surface right here is facing towards you. That would be a gamma 90 degrees. It is facing west. And even this surface right here, it's tilted, the component that is in the plane, which would be like that, would also be facing west. Okay, let's get those numbers up there and get going. Again, if you can figure it out on your own, fantastic. If you want to go step by step with me, that's just fine too. So our ultimate goal oftentimes when we have solar is to work out this number here. Hey, for our collector surface, how are we doing compared to 200? That's the total available on the horizontal. How about for our tilted surface? How are we doing? So breaking it down a little bit, we can figure out these things right here. So I'm just going to go step by step and work them out and help you either work it out yourself or follow along. All right, so just going through the math, G direct on the horizontal is 160, and we're going to divide by sine 30, so we get 320. And I'm going to leave out the units right now, watts per meter squared. So what's that telling us basically, without a lot of information, a lot of detail, is, you know, the sun's pretty low in the sky, okay? And if we were to take a collector and tilt it so it was exactly perpendicular, our intensity would be better. It would be a lot better than 160. All right, so where are we headed then? The next thing we want to do is we want to get the angle of incidence. So what is the angle of incidence? So that requires doing a drawing. We may take a look at three-dimensional drawings later on, but right now we can pretty much do what's called a side view in this case. So basically what I could do is I could draw my surface in, and its tilt is 90 degrees. So let's say like there's the horizontal there like that, and then the surface would be vertical here like this. A lot of times you'll see the shading in here like this to indicate, look, this is the surface is over here on this side. That's what we're interested in. And there's that normal there, line there like that. So that normal line. Okay, and all this solar that's coming in is coming in at 30 degrees above the horizontal. So this is going to be 30 degrees above the horizontal too. And so our angle of incidence is 30 degrees. Okay, again, so a little bit of review from last time. That should be easy enough. And then let's go ahead and figure it out. So GD, which I indicated with a formula earlier, could be done as GD theta. What is the intensity of the direct radiation on this horizontal surface? Okay, so it would be 320 coming on a surface that directly faces the sun, and this surface here is a bit off from directly facing the sun. So what we want to do is modify that. So for this one right here, we're going to do the normal direct times the cosine of the angle of incidence. And so the normal direct is 320. And we're going to do it by the cosine of the angle of incidence, which is 30 degrees. Okay, I can't do that in my head, but you know, it should be pretty high because the angle of incidence is not large. And I'm getting 277. I'm getting 277 watts per meter squared. All right, again, leaving off the units. All right, and then this last thing here, what I'm doing is saying, hey, approximately what is the total G? And I'm going to put that on the homework, and please don't stress about that. But I would encourage you to think about how would we go in going about approximating it. So maybe trying to do a little bit more complete picture of it down here like this. So there's the ground. Here's our collector surface. Maybe it's a window or something like that. Okay, and so using red to indicate solar, okay, this solar that's hitting the surface here like this, that would be the direct stuff, okay? But then in addition, you know, there's the sky dome above here like this, the sky dome, and there's diffuse stuff that's coming off the sky dome. And at any particular point, there's diffuse that's going in all directions, all right? And that's the idea, again, that the sky is scattering solar. All right, so this scattered solar over here like this, it's not going to hit that surface. It's not going to hit that surface. But this scattered over here like this will hit that surface. So, hey, how could we approximate it? Well, in this case, it's not so bad to actually go about approximating it. You can see, hopefully, that this surface over here like this side right here like this, is exposed to half the sky. And so it's not an unreasonable approximation to say, okay, taking a look at an earlier bit of information, the diffuse on the horizontal is 40. And that would be on the horizontal, that's exposed to the entire sky. So this surface right here is exposed to about half the sky. So we could say, hey, the diffuse on our surface, which I'll just do as G sub D, is going to be about half of 40, which is 20. And so our total would be about 297 watts per meter squared. Okay, so ultimately, you know, hopefully maybe this time next week, we're going to be really good at nailing what that is. But that's a really good approximation. If you go back to the beginning of the problem, we can evaluate what we were doing earlier in the semester. Earlier in the semester, the problems where I had you guys work out, hey, or even for homework number 6, how much area do we need for a PV system or a solar thermal collector? We assumed that our collector was horizontal. We assumed our collector was horizontal. So we, as far as our available solar, we started with GHI. Okay, now we tilt it up, and instead of just 200, we have 297 available. So tilting can make a tremendous difference in the performance of the system or how big it needs. Okay, so thinking a little bit more about angle of incidence. We can have an angle of incidence because of what's going on vertically, like the direction that the surface faces can be off from the direction the solar rays are coming in the vertical direction. So like this could be horizontal, and the sun's rays could be, even though I'll get it in there, even though you can't see it all very well, can be pretty high, and so there'd be an angle of incidence. But it can also vary what's going on horizontally. So basically, to see that, it's really good to do an overhead view. So this would be the sun's rays coming in, and let's, again, the yellow line represents south, so this collector is facing south. Well, so what if the sun was low in the sky and came in from the west? Okay, that would be in a case where you had something like this, right, where the sun's coming in from the west. And you could see how you could actually get an angle of incidence between the sun's rays of about 90 degrees. So right now here, this one's southwest, okay? And then over here, I've got the sun rotating, and it's coming in from the west. And again, the angle of incidence is the angle between the normal line and the incoming rays. So we would have an angle of incidence in there of 90 degrees. All right, so let's take a look at a case where the incident rays are not coming directly into the collector surface, not because of what's going on vertically, but because of what's going on horizontally. And to do that, we'll draw an overhead view where we imagine we're above the collector here like this. We're above the collector, and we're looking down at the collector surface. Here's an example where there's an angle of incidence because of what's going on horizontally. So again, it'd be great if you guys could interpret this yourself, or maybe pause it and read through it and see if you can figure out what's going on. Our goal is for this surface, which the information for the surface is given down here like this, okay? How intense is the direct on that surface? And can we approximate the actual total on this surface? Well, the very first thing you're going to do is going to be able to get the angle of incidence, or an essential thing. So what I encourage you guys to do is pause the video and see maybe if you can do a three-dimensional view of this. So that would be the first picture over here, the three-dimensional view, and then see if you can do an overhead view as well and come up with the angle of incidence. A little bit of a mistake on my part. I say let's come up with a number for the angle of incidence. For now, the best we can do is get a really, really good approximation of the angle of incidence. Okay, so hopefully you're working on that and getting a drawing for what's going on. And I'll get my drawing up there in just a second. Okay, crude drawing, and if you had more time, you could do a little bit better job of it. But the blue represents a surface, so it's facing south, so it would be a vertical surface there like that. So the normal line would actually be coming out towards the south, all right? Okay, well, where is the sun? The sun is, its gamma is 89 degrees, so that means that it's almost in the west here like that. So that sun is in the west. Its alpha is 1 degree, so it's virtually at sunset. So this sun is virtually setting right over here, and there's the incident rays are coming in and hitting this surface right here at a very large angle of incidence. They're way off from straight on. Could we come up with some sort of estimate? Well, you can probably get pretty close if you were to criticize me and say, look, that is not representative there. That's a lot bigger than 1 degree. This sun is virtually in the west. Okay, so how about an overhead view? What if we were looking down at this surface right here, and we saw the path of the sun? So that's easy enough. The sun is in the west. So if this is an overhead view, if this is south, okay, and then west would be down here like this, the sun is virtually coming in from the west. It's virtually coming in the west. And so basically our angle of incidence, okay, is basically about 89 degrees. So our angle of incidence in this case is about 89 degrees. Okay, that is approximate because I have the sun just very, very slightly above the horizontal. So actually it would be bigger than 89 degrees. There's a mathematical way to get that. We'll get to that next, but this is good enough for right now. Okay, so let's get at it. Let's go ahead and see if we can figure out how intense is the direct on this surface, how intense is the direct on the blue surface. Obviously, it is going to be very, very low, but we're going to work that out. And then the bottom line is figuring out this number. Let's maybe like verbally discuss what that number is going to be. Okay, so I'm going to be getting through the work, and hopefully you're doing it yourself really quickly. And let's see. Okay, in order to get direct on a surface, the first thing we need to do is get the normal direct. So there's our equation. There's a total of 10 on a horizontal surface, but 8 of that is diffuse. And if you think about that, that makes sense. Basically, the sun right now is really, really low in the sky. So the direct rays are not going to produce a lot of intense solar on a horizontal surface. So most of this 10 watts per meter squared should actually be diffuse, not direct, and that's what the numbers reflect. So let's put that in there and see if that makes any sense. I'm going to do 2 divided by sine of 1. And again, just because of whiteboard space and time, I'm being a little bit lazy with my units. And it'd be great if we were in class so I could get a check from you guys. But I'm getting 114.6 watts per meter squared. And that's kind of interesting, okay? Basically what that's saying is that if I had a surface that actually directly faced to the west, right there like that, directly faced to the west, the solar would be in pretty intense. And of course, you probably experienced that. If you go out, like say like if you're at the beach or something like that, and you face the sun right as it sets, you can feel those solar rays on you because you are actually directly facing the sun, and it's pretty intense. So even though the solar on a horizontal is low, the solar on a surface that directly faces the sun is going to be high. Okay, but then how do we go about it actually figuring out the direct on this surface? Then we're going to take the normal direct and multiply by the cosine of our angle of incidence. And our estimate for the cosine of angle of incidence was 89 degrees. So okay, so there it is set up, and I'm punching my calculator. I'm doing that times the cosine of 89 degrees, and I should get a really, really small number. Kind of interesting to think about it. I ended up getting back to 2 watts per meter squared. I ended up getting 2 watts per meter squared when I got back to it. Okay, how about the total that's going to be on this surface right here? Well, that's a pretty interesting question. We know that the diffuse on the horizontal is 8. But this surface right here is that diffuse on the horizontal is due to solar from the sky, and the horizontal, of course, is exposed to the entire sky. This is not exposed to the entire sky. So there's going to be an additional beyond 2, but maybe not that much. And we could actually approximate that. We'll get to that later on. Again, right now, this math is the basic number. Okay, so to get a more precise way of figuring out angle of incidence, we need to think, well, look, the sun can be off from coming directly into a surface because of what's going on vertically. How high is the sun in the sky? And also what's going on horizontally. So that latter thing, how far off are the sun's rays from direct horizontally is easy enough. But let's just start by just visualizing that this right here represents the normal line. There's our collector surface. There's the normal line. Let's imagine that this is pointing south. So this is pointing south. So what if the sun's rays were off by 0 horizontally? Well, that means the sun would be in the south. So if you took a look at an overhead view, imagine you're looking down on the collector, the sun's rays would be coming in there like that. Even if the suns were above the horizontal, in the horizontal direction, there would be 0 rotation. So this is 0 rotation, and still this is 0 rotation horizontally. Okay, now as the sun goes over into the west, we get a larger and larger angle between the sun's rays and the normal line. So in this case, we would have some sort of displacement between the normal line and the incoming rays horizontally. Okay, well, basically what we're going to do then is we're going to take a look at the difference between the direction the collector faces, which is the normal line, the direction the collector faces in the horizontal, and that's indicated by gamma, and gamma S is the sun's rays coming in. So the difference between gamma and gamma S is going to give off how much we are off horizontally. So let's practice that a little bit and then put it all together with a formula that gives us a precise calculation. All right, well, let's take a look at an example that's put pretty theoretically. I got some information about the sun, and I've got some information about the surface. And roughly speaking, our question is, okay, those sun's rays, how far off are they in the horizontal plane from being direct? How far? And we want to come up with a number in this case. We want to be pretty precise. You know, it'd be great for you to look at those numbers and just come up with in your head, but it's also worth it to be able to do a drawing. So what I want you to start with is thinking about doing a 3-dimensional drawing where you try to picture what's going on. So I got south there, and you give it a quick try. I would like you to pause the computer and take a look at that, write down that information and see if you get that drawing. Okay, the 3D drawings are a little bit challenging, But basically the sun is in this is west over here like this, and the sun is in the southwest. Alpha is equal to 0, so the sun is actually setting, and those rays are basically skimming the Earth's surface and hitting there like that. Okay, so what is the angle of incidence between these incoming rays and the normal to that surface? You know, I can see it pretty well because the normal to the surface is actually to the west. I have that the gamma for the surface facing direction is 90 degrees and it's to the west. And so look, it looks like it's 45 degrees in there like that. Okay, what you're going to notice as you do these drawings is that if you're trying to figure out, again, how far off the sun's rays are horizontally, an overhead view is good enough. It makes it really, really clear. So why don't you go ahead and try to do an overhead view where we're going to make this dimension south and this dimension west here like this, and come up with what the angle, how far we off are horizontally. I'm doing it myself. And there's not a great, but a pretty complete drawing. The red represents the sun's rays coming in from the southwest. That blue thin rectangle represents the surface and it's facing west. That could be a window or a collector or something like that. I tried to get a dotted line in there that represents the normal line, and how far we are off horizontally is that angle in there that is 45 degrees. Okay, and what you're going to see as you go through it with a formula, basically that if you take the difference, and if you guys got to excuse my writing since I'm sort of off at an angle here, if you take the difference between gamma and gamma s, okay, you're going to end up getting that angle. Then you're going to get out how far we off horizontally, that's a good start. Let's do. All right, so in this case, the information is a little bit more like what you might receive if you were doing some design work. Okay, so I've got some information about the sun. Its alpha is 40 degrees, so it's pretty high above the horizontal. Our collector is tilted at 40 degrees above the horizontal, and it faces southwest. So, hey, the 3D drawing's a challenge, but I want you to give it a quick try, and then we'll do the overhead view, which I have over there to the right. And again, the question is, hey, how far off are the sun's rays horizontally from directly in? And in some cases, we're going to get 0 degrees. It's directly in. The amount of horizontal displacement is 0. So go ahead and have at it. This drawing here, be patient with yourself. Be patient with me. It's not going to look great. And then try to get the other drawing there, and we're going to try to come up with a numerical example. Okay, so being a little bit generous with me, there is, the first thing I'm trying to do is getting the sun in. And so that's a rotation of 20 degrees. The sun hasn't quite reached noon. Noon is when the sun's in the south, so the sun's a little bit before south. And of course, it's elevated up a bit, 40 degrees. So we're going to have a sun coming in to our point of interest right there like that from that angle. Pretty imprecise. All right, the next thing to do is to try to get our surface in there. And so the first surface faces southwest, and there's west there like that. Okay, so basically the way you would think about doing it, okay, is the surface is basically facing southwest over there like that. So a little bit messy drawing, but what I can do is imagine a surface here like this. That's neither facing south nor facing west. It's facing there like that. It's facing essentially that direction there like that. Now, not only is it facing southwest, but it's also tilted. Its tilt is 40 degrees above the horizontal. Okay, and that is a really great challenge artistically to try to get that tilt in there. And I'll give you a couple drawings to look at for homework number 7 where you can get that. But basically, it's facing that way like that. Okay. Now, how about the normal to it? Well, its normal would be coming out at an angle, excuse my fingers, but its normal would be coming out at an angle up like this. I'm sorry if I can't get in there, but basically, hopefully you can see a little bit what's going on with that normal coming up there like that. But we are interested how far we off horizontally. So we could just go ahead and draw in a dotted line within the horizontal that represents 45 degrees there like that. So it's facing that way like that. So that could be a gamma for the surface. All right, so how far are we off? Well, we've got 20 degrees here, and we've got 45 degrees there like that. So we would say horizontally, we're off by 65 degrees. The sun is over here like this, the surface faces like that, we're off by 65 degrees. Of course, it's a lot easier to see in the horizontal dimension, pardon me, if we were taking an overhead view. So from an overhead view, let me just shift the screen a little bit. From an overhead view, okay, the sun's rays are coming in from an angle of 20 degrees. So again, we're looking down, 20 degrees, it's kind of like we're looking down like that. And the sun's in the southwest, so it's coming in here like that. And so we have a difference of 45 degrees like there, and we have a total of 65 degrees. Okay, so our answer is 65 degrees. You'll note in a little bit that the textbook does that, how far we off horizontally, by gamma s minus gamma. So strictly speaking, according to the book's formula, we would say that, writing that down again, pardon me, gamma s minus gamma. How's that going to turn out? Well, gamma s is equal to negative 20 degrees, and gamma is 45 degrees. Sorry about my writing. So we actually, strictly speaking, get a negative 65 degrees. So turns out that that negative is not important mathematically, as you'll see in a few minutes. But it's basically giving the same result. We're off by 65 degrees either way. All right, so all that was precursor to the fundamental question we're going to have is like, in a case like this, what's our angle of incidence? All right, so we're trying to get the angle of incidence, and there's my crude drawing. We know that there's 65-degree offset by the sun horizontally, but there may be some offset vertically. And this drawing right here is an attempt to figure out what's going vertically. So basically, the black represents our collector surface, and beta is how much it's tilted. It's tilted 40 degrees above the horizontal. The little blue line, that's the normal coming out. And then my magenta or pink line is the incoming solar rays. And if you look at that, I'm thinking that it doesn't look like it's directly in. Now, my drawing's not perfect, and certainly we could take the time and do the math. I'm going to ask you to do that on homework number 7 to see how far off we are. But to me, it's looking like we're not directly in. So we're off by 65 degrees horizontally. It looks like we're off by a bit because of the combination of beta and alpha. And how much is that going to turn off? How much bigger are we going to be off by 65 degrees? All right, well, that is the formula right there. That's our formula of the day. Please don't ignore the conceptual stuff. The conceptual stuff that we worked on earlier helps. But that is the formula we want to be able to work on. We want to be able to get the angle of incidence or do some good problem solving. So take a second to write that down. I hope that you look at it and say, oh, that looks an awful lot like a trig formula I learned in pre-calculus, and that's absolutely right. If you just take this last section right here and ignore it, that is a basic trig formula. That expression there is a basic trig expression for an identity. And then over here, this last little bit is the adjustment due to what's going on horizontally. So please don't worry about that. Get that formula down. Let's go ahead and plug and chug and work and see how that turns out. So I'm going to be doing it on my calculator. You do it on your calculator, and we'll see what we end up getting for theta. All right, so I've got the math set up, and I just went ahead and substituted and substituted and substituted and got those numbers in there. By the way, this example is going to turn out to be initially a little bit of a strange number. For me, this is a big challenge. My three-dimensional viewing skills are not great, but I encourage you to maybe make a model yourself where you take the angles and see whether the numbers make sense. So I'm finishing it off really quickly. I'm going to just pull out my calculator and do it, and hopefully you've done it yourself. 0.4924 plus 0.4924 times cosine negative 65. And then if you think about it with that negative 65, hopefully you can see it's really not going to matter what order we do this in. whether we do gamma S minus gamma or gamma minus gamma S, we're going to get a value, and the cosine of a negative number and the cosine of a positive number are the same, so it doesn't really matter. This is basically how much we're off by horizontally. Negative or positive doesn't matter. Okay, when I chugged in my calculator, all that turned out to be approximately 0.7. And so when I go through it, I get an angle of incidence of about 45 degrees. So it's off by about 45 degrees, which seems wrong given what I was talking about earlier about this angle of incidence being a combination of how off we are horizontally, 65 degrees, versus how far we off are vertically. And it would seem like it should be bigger than 65 degrees. But there's some interesting things geometrically going on. I think on this example, the thing to do is to follow the math. And then to finish off lecture today, let's do one more example where we change basically the same situation, but we change the tilt of our surface to make it a window, all right? So make it a window. So let me just get that up there, and we'll do one last example to see how it all works out. Then I'm going to be, again, I'm a little behind. I need to get you guys on a variety of things, I know. I need to get you guys homework number 9. And then on Wednesday, probably Thursday, we're going to, during meeting time, have essentially a computer lab meeting where we do some Excel with this. So make sure that you have your formulas, including this particular formula here. If you could do just a bit of work on homework number 7 before Thursday, that would be great. Okay, so I've taken the same problem and I've changed it to beta equals 90 degrees. So that means that this surface now is tilted at 90 degrees. So how are our pictures going to change? Well, this one's a little bit challenging. I'm not going to take the time to do it, but the sun's still in the same position. The surface is now vertical. All right, this picture obviously would change. This black line would now actually be a vertical line like that. Okay, and I can get that in there really quickly like that. So there's that window there like that. And we have this. We have the sun coming in at a certain angle of incidence between there. Okay, before we spend a lot of time plugging and chugging, let's take a look at that formula and see if anything's going to be easier because beta is equal to 90 degrees. Okay, and you can see that the first term's got sine alpha, cosine beta, and the cosine of 90 degrees is 0. So this first term here is going to go away. So all we have to do is do this stuff over here. Okay. And let's see if that's going to be any simpler. We got cosine alpha, and then we have sine beta. Sine 90 degrees is 1. So what we're going to end up with is cosine alpha and cosine of that other term. So I would encourage you straight to go to a step where you just write the remaining terms, and I'll put it up there, and we'll see if we can make sense of how this one's going to turn out. Okay, so in this case, the formula simplifies to that term right there, that one single term, and we can make some sense of it. This 65, again, is how far we are off horizontally, and then this 20 degrees is how far we are off vertically. If you take a look at that picture over there like that, now we have this new tilted surface, tilted at an angle of 90 degrees. The suns are coming in there like that, and for a vertical surface, essentially how far are we off? R is the same as alpha, so we're off by 20 degrees. So what we're going to do is we're going to see, in this case, it's actually going to work out that we're off by 65 degrees horizontally, and then we're off by a little bit vertically, and just crank the numbers and see how it turns out. I'll do it on my calculator, check our work. Okay, my calculator for that term right there gave me about 0.397. So I've got the cosine of my angle of incidence is equal to 0.397. So working that out on my calculator. Okay, I got an angle of incidence of 66.6 degrees. Okay, and now actually I think that one's a little bit easier to make some sense of. We're off by 65 degrees horizontally, and then we've got a little bit of elevation, which makes a difference in that 66.6 degrees. So in sum, that's the math. That's our equation of the day. My idea of saying, look, we're combining how far off we are horizontally by how far off we are vertically. You got to be careful that the numbers don't work out always to entirely make sense that way. But nonetheless, you do want to think about how far off we are vertically by doing horizontally by using that expression, and an overhead view does it. Get a little bit of practice on homework number 7. And then on Thursday, we'll do some Excel computer work where we try to put this all in a spreadsheet and get an overall feel for performance of a collector over the course of the day, given our choice about how we end up orienting that collector, where we end up taking the normal line and pointing. All right, please email me questions, and we'll talk again on Thursday. Take care.